Hello, everybody. My name is Zarrin, as Dominic mentioned. This is the second presentation of the topic, formal methods in safety-critical systems. Recall from the last presentation, I covered this definition of safety-critical system and the application area of these systems. I mentioned specifically safety-critical system, defibrillator. Among the safety-critical system, I covered the medical systems, and among the medical system, medical devices. And for medical devices, specifically software medical devices. I went over FDA and Canada regulation and device classification, which also Naghmeh and Usman will mention about it today. I covered the formal methods, the definition of formal methods. But today I will focus on a specific software specification model for medical devices and the risk analysis of software medical devices. Finally, I'll go again to the defibrillator example and I investigated the software safety analysis of the defibrillator, and I speak about the lack of formal method in defibrillator and in general the implementable medical devices. So again, recall from the last time, a safety critical system is any system who puts in danger the human life and the environment. Among the safety critical system, the medical devices are important also. And based on the FDA definitions, there are three classes of medical devices. Class 1, Class 2, and Class 3. As the class number increases, the risk will increase, and as we have the higher risk, it is more important to find out what are the hazardous behavior of the system. And we also had the software medical device definitions. It's good to mention that last time we went over some example that what are the leeches? Leeches being considered also a medical device, but a Class 1 medical devices. And for example, the information system, the blood bank information system, are considered a Class 2 medical device because the data that they contain are important and is a safety critical data. This is a model for medical devices for the requirement specification document. In the requirement specification document of the model, we should have these different sections. First of all, we should define what is the purpose of the document. We should say what is our device. Is that critical? Is it a self-contained device or it's an embedded one? We should go to product overview and mention the features of the product. What are the features of the product? Who uses the product? And some other general things about the product. Then we have the processing environment, which is development and maintenance part of the environment. And then we have the interface requirements of the system. The interface contains user interface, hardware interface, software, and communication interfaces. The other important section is medical device functions. This is actually what all the information that a designer needs to develop the software. And it contains several subsections. The main important one is the functional requirements of the system should be defined here. The performance requirements should be defined. The risk analysis and some other subsection. I have the detail of all these subsections in the longer version of my presentation. Finally, we should define in the definitions all the terms that we use in our software, and the terminology should be defined here. Among all these sections, I'll focus on the risk analysis of the software medical device. So risk analysis has three important things. We should know, first of all, why it is important then what kind of software we should do risk analysis for, and what in general, I just mentioned in general, what should be done for risk analysis. So there are two reasons. First of all, the software medical devices are increasing day by day. Even the number of medical device parts that also is used in the medical device, or part of it also increases day by day. The second reason is that even if your product is has many parts of electromechanical and electronic parts, even in those kind of products, the software can consume 70% of a multi-million-dollar development budget. And even the simple devices with basic user interfaces take 40 to 50% of the budget of the software. Second, in what kind of software it applies? In three kinds of software in general: the application-specific embedded software, the commercial off-the-shelf software, or those libraries that exist and can be used in the software medical devices, and finally, in even the software development engineering tools like case tools, the risk analysis should be done. And what should we do for risk analysis? Generally, first of all, we should find out what are the risks, what are the faults actually, and the consequences of those faults. Second, we should take appropriate actions to minimize those risks. And third, the developer should verify the software finally to be sure that the risk has been minimized. So there are several key concepts regarding the risk analysis of software medical devices. Among those key concepts, in general, medical devices must fulfill operational requirements and with the focus on patient and provider safety. And there are several initial engineering tasks that should be done to get the operational requirements. These are requirement analysis, architecture specification, and initial risk analysis. Initial risk analysis specifically involves us how the software failure ended to a patient hazard and what are the consequences of it. For example, the first thing to do the initial risk analysis, we should provide a table, an index table. This is an example of the initial risk analysis. There are two hazards defined here. Both of them are patient-borne, but only one of them is due to the software failure. We should say what is the probability of that hazard, and final, we should go and define the minimum response if that failure happens. And I gave you a general overview of what should be done for risk analysis. This is actually a detailed version of the risk analysis process for safety critical softwares. So, but basically still it goes to the same category of general overview, finding the faults, minimizing the risk, and finally verifying the system. So we have two levels of reliability for the software. The first level and the best one is highly reliable software. But even if your software is not highly reliable, you want it to be trustworthy, which means in case of failure, we want that the behavior of software be predictable. And having that, predicting the behavior of the system, we can minimize the risk that exists in the software, so having a lower risk. So you don't have a highly reliable system, but at least you have a trustworthy software system. So usually in medical devices, the device is considered in a safe state when all electromechanical operation is stopped and an alarm system is activated. So an example of a highly reliable software is a US Federal Aviation new air traffic control system. But in general, all the highly reliable software includes formal verification and validation process. And they cost about $500 per delivered source line. But in compared to that amount, medical device software seldom are more than $90 per delivered line code. And actually, even in highly critical life-threatening medical devices, the medical device industry does not support enough funding for development and the formal specification and the formal verification of the software. So given these realities, the medical device industry and the developers usually tend to go for the trustworthiness instead of the high reliability or the NASA level reliability. So recall again from the last time, this is the definition of the formal methods. Formal methods are mathematical and logical formalization, and they used to prove the properties of the system are satisfying the expected behavior of the system. The properties of the system contain functional properties and non-functional properties, which is safety and security. They also tend to find the defects early in the software lifecycle, in the requirements phase. Oops. So these are some examples of the computer science areas that applied formal methods in different areas: databases, devices, hardware, medical. In the medical area, this is an example of the clinical neutron therapy system at the University of Washington, which is called cyclotron controller, uses the formal methods. Actually, I don't know enough about the details of all these things, but they exist as the references exist at the Clark paper. So, but I would like to specifically focus on the defibrillator software safety. The defibrillator is a shock delivering system which contains a battery, 2 sets of leads, an electronic part and a programmer part or a software part. The leads are delivering shock in case that the heart rhythm is not proper. So this is basically a defibrillator. At that part, you see the battery. At the middle part, this is the electronic part. These are the leads. And actually, the programmer or the software part, which sits on a laptop or a small notepad computer, can be in the physician office. This is an overview of the management system. The programmer part is interfacing with the pulse generator or the electronic part. And these are 2 sets of leads. One is sensing, and the other delivering the energy or shock. At the University of Minnesota, there were several researchers decided to go do the software safety analysis of the defibrillator to find out if the defibrillator is safe. They conducted a systematic software safety analysis to find out the faults and then modify the software faults and then finally verify the whole software safety. The software safety analysis is not a separate function. It should be considered in these kind of devices. For example, in the defibrillator, it should be considered as an integrated part with the system safety analysis. So the electronic part also is important. And the modification process should be practical because every developer has a different technique to develop. So why the software safety analysis in defibrillators difficult? First of all, we can't go over the code line by line to find out the faults. And even for these kind of devices which are highly safety critical, the fault tree is very huge and it is a massive tree. So it's nearly impossible to understand the whole fault tree. Also, there are different notations for requirement specification, data flow diagrams, state transition systems, and also English statements. So to find out what are the software functions, we should go to the data flow, control flow, and state transition diagrams, and to find out what are the conditions that makes the software fail. 2 parts are important. Software to system interface is important, and also the software itself that causes the interface faults is important. So Because of that, having a very well-defined and well-specified software-to-system interface is critical. Also, as the defibrillator software safety analysis given to different engineers generated different fault trees. Even the hazards are the same and the hierarchy of the causes are the same. So having a formal specification is required to make sure that these fault trees are consistent and they are complete and contains all the faults of the system. So these are the top safety hazards of the defibrillator. For the patient dying fault, there are several reasons, there are several faults, and for the specific one I chose, I showed these 4 may happen, and when at the case of no energy or no shock is delivered when the patient needs it. So I don't go to the details of all these faults. But finally, after finding the faults and modification needed to minimizing the risk of those faults, finally we need to do the verification. Currently, verification is done by walkthroughs to check for correctness, completeness, and consistency. But having a formal specification of the software and system makes it possible to use the tools to do the formal verification. And the tools also assist in deriving the fault trees from the formal system and the software specification. So, in general, using the formal methods helps specification to be challenged and explored, and also it helps us to find the defects that happen in the software early in the requirement phase. And in one sentence, the formal methods define if the specification says what it should, then the following ought to follow. And this can be formulated by formal methods and proved automatically by tools. So this is a summary of my talk. These blue parts I defined on the last presentation, and specifically today I went over a software specification model for medical devices. I defined risk analysis for software medical devices. On the formal methods part, I went over the computer science application areas, used formal methods. I went to the specific example of defibrillator software safety analysis, and finally I went with the lack of formal methods in defibrillator software safety part. And these are the references, and thank you.
Slide 9, you had mentioned that medical device software will cost more than $90. So I was wondering, do you mean a component of the medical software, or do on an average an entire system, does an entire system cost $90, more than 90? Like, costs usually less than $90.
The question is that, is the $90 the average cost of the medical device per line, or
is it the cost for the entire system, or is it just cost of the software involved in that?
Or the cost of the software that involves? It's just the cost of the software. It's the per line of code. This $90 is per line of code, source code that is delivered, actually. It's not regarding any other part. Because actually, as I mentioned, the software consumes about 70% or even at least 50% of the budget of the product.
So would that mean that on an average a medical device doesn't cost more than, say, $200?
No. It's, first of all, this is per line of code for software part. The electronic part is very expensive. So that's probably why they don't use the formal verification or very expensive part of it, because the electronic part itself is very expensive. Though they tend to bring the cost down. So they don't put that much budget on the software part. Yep.
My question has to be on slide 92.
On slide?
On the same slide.
Okay, good.
And I'm wondering about the last point. So you're talking about economic realities and trying to achieve the trustworthiness rather than the reliability. I'm wondering if you could give some more details about that. What is this economic reality that they're facing? And if reliability is better than trustworthiness, why isn't the FDA insisting that they achieve this NASA level reliability?
The question is that why, if the high reliability is important, the FDA do not ask the medical device industry to reach that high reliability. Actually, the problem is that, as I mentioned, the medical devices are expensive. So, and the software part is one of the important parts. If they want to put that much amount on the software part of the system, so it costs too much. And because you see, at the NASA, when it applies the high reliability to the system, it goes for a kind of racket, or for the federal aviation of the system, there is one system. But for the medical devices, it could be reachable by the patients, and the normal people could be able to buy it. So they try to have the second level of reliability, which is the trustworthiness. They want to be sure at least it's safe, it goes to the safe state, because they can't reach the high reliability. And the FDA probably can't force the medical device industry to have the high reliability for the whole devices, because the cost will be huge. So they want the medical devices to be accessible by all the people. So that's probably why they don't put that much money on the software part of it to get the high reliability.
Just one question. What's the research direction here? I mean, what have we gotten down to in terms of the goal of the project? Repeat the question.
Yep. Actually, the question is that what is the research orientation of the project? The investigation first of I did was why the formal methods should be used on the medical devices, and specifically the defibrillator, as I went through it. And I mentioned where are the lack of formal methods at the defibrillator software system. So why, if they use it, they get to the because those kind of devices are very important in compared to the other, for example, the medical devices, because they are attached to the body of the patient, and any one of those hazards that I mentioned can cause the patient to die quickly. So that's why I think those kind of devices should be considered as a high reliability of system, like the kind of the NASA level reliability. And I think the industry is going toward that way, but they didn't reach that. The other thing is that so far the formal methods were expensive, but it's tending to the cost of those methods coming down as the research goes. So my point of view was that these kind of devices are very important to use formal methods. And what are the causes of lack of formal methods in those systems?
Okay, your point is that we should apply formal methods to this area of verifying this level of safety critical software. The question still is, though, if formal methods as they exist now are adequate, that's just an application. I'm wondering, are there any aspects of this where one would develop more advanced formal methods, techniques, or alterations in application of those techniques, or some aspect where it was not just an application of formal methods? Is there anything there? I'm
not actually sure if there is for example, this part is not an application or it is something specific. I think it is something specific that contains the formal methods itself as a kind of improving part of the medical device industry, or considering some specific things regarding the formal methods, not an application of those methods as the other computer science areas, because they tend to bring the cost of these ones down. So probably they should use a specific formal method technique. So far, I couldn't find in the literature the specific formal methods that use in the medical devices. I just saw several examples like the cyclotron ones, which they use the Z system, which exists in actually literature. But I think to bring down the cost of the medical devices, they should use a specific version of formal methods, customized and tailored for the medical devices.
What I hope in the final summary in your project that you would incorporate some thinking about that. But anyway, thank you for the presentation.